Swayam Prabha. Digital India. Educated India.
So, we are discussing some applications of continuous Markov process in the last few classes. The problem we handled in the previous class is that is a suspension of particles which we call colloidal dispersions made up of Brownian particle in a liquid, and they are actually standing in the gravitational field, and then each particle sort of sediments due to the balancing due to diffusion by Brownian motion versus the gravity pulling it down. And we predicted that in the absence of interparticle interactions in a very dilute case, each particle is subjected to gravitational force and diffusion, and then we predicted what is the concentration profile of these particles, and we found that it is an exponentially falling profile. Okay, and the rate of this exponential decay is related to the material property, like its mass, its density difference, temperature, and so on. So this is one scenario. Now I want to take you to another scenario, very similar situation. You have a suspension, colloidal dispersion, let's say nanoparticle or micron size particle dispersed in a solution. In this case, let's say there is no gravitational effects. The particles are too fine that there is no gravitational force acting on it. On the other hand, we are thinking about very dense system, okay, where the particles are actually too close to each other, and then they can encounter each other also. Okay, so now we are talking about a denser situation, higher concentration limit in the absence of gravity. In this case, what might happen, what is seen in experiment is that these particles, once they come too close to each other, due to van der Waals forces, they would stick together, they would aggregate. Okay, if it's a liquid droplet, they can even coalesce and become one big droplet. Okay, so now I am talking about a binary collision, two particles coming together forming one droplet. When this droplet meets more such particles, you have a cascade of aggregation, you have a cascading effect of coagulation. And now in this problem we want to predict what is the concentration of each species, what is the concentration of monomers, doublets, triplets, quadruplets, and higher order aggregates, and how the system evolve due to this aggregation. Okay, now this problem, okay, we are talking about colloidal suspension, highly concentrated, and they undergo Brownian motion, and when particles come close enough, they can aggregate. Here there is no external field like gravity. If you want to add gravity, you can add, but even this itself is an interesting problem to study. So here our question is to look at how the concentration of each species varies with respect to time. Okay, in other words, if you know this concentration of each species, you can also find what is the mean size of the aggregates. Initially you start with all particles identically sized, monodispersed, same size, but then because of the aggregation, because of this coupling, particles will start growing, number will keep coming down, the total number decreases, but the average size will keep increasing. So you want to predict what is the average size of the clusters, what is the size distribution of these clusters, etc., etc. That's the question that we want to solve. Apparently this problem we can actually solve using Brownian motion theory or the continuous Markov process. After all, the particles are diffusing around, it's a Brownian walk, and then we can find what is the distributions are, what is the encountering probabilities, and how to get the rates of the collisions between two particles, and from there onwards we can study. So that is the problem I want to focus today. So the previous problem was sedimentation. Sedimentation, where the particles are very dilute, okay, and there is a gravity acting on them, and then there is a equilibrium distribution for the concentration profile. Okay, you see that over time you will have highly concentrated particle at the bottom, and then as you go up, the concentration decays exponentially. Okay. And so here we did not assume any sort of interaction between the particle. Each particle is on its own in order to sediment and in order to diffuse around. Okay, so this is one problem we have seen. Now what we are talking about is called coagulation or aggregation. Here what we have is, we have a system no gravity here, but I have too many particles here. Okay, so I have so many particles and they actually diffuse around. Okay, by the way, if you ask how did we even prepare in the first place, well, there are different methodology by which you can create these particles. Okay, and you can make them stable. You can actually even make them stable against this aggregation. Now to see aggregation you have to add something. Okay, for example, if these particles are, let's say, stabilized by because of electrostatic interactions, you would add electrolyte, you would add salt to screen the electrostatic interaction, so that when particles come close enough they can aggregate. Okay, so adding salt to induce instability of the suspension. So we are talking about at time t equal to 0, something is added to this stable dispersion, otherwise then the particle starts aggregating. Until then they are stable. Okay, so at time t is equal to 0 we are adding an electrolyte. So what happens is that when this particle and this particle come close enough, okay, so when two particles come close enough, they form one big aggregate, right? So we say this is like monomer forming a dimer. Now of course this dimer can encounter another monomer and can become an aggregate having 3 times the volume of the primary particle. Okay, so essentially we can write this set of process as a chemical kinetic equation like this. An aggregate having I number of monomers interacting with another aggregate having j number of monomer, forming one bigger aggregate having I plus j monomer. So essentially this problem can be cast into a form of a chemical kinetic formula. If you recall, we did this problem in the chemical master equation also, aggregative growth. So now we are looking at the same problem from a continuous Markov process with some additional information that we can draw from here. Okay, so as I said before, this process continues to happen, and then as a function of time we want to predict what is the concentration of monomers, dimers, trimers, tetramers and so on. So that's the ambition. Okay, that we can get by looking at an equation like this. We can write an equation similar to chemical master equation and then solve for each species concentration as a function of time. Okay, so before we get there, there is something called this rate constant. Okay, we need to know what is the rate constant of collision between A and AJ. Generally when we dealt with chemical kinetics, we did not pay much attention to the rate constant, because in chemical kinetics the rate constants have a different physics behind it. Okay, there is a transition rate theory, there are a collision theory and etc. etc. We did not pay much attention to those theories, but here we are not talking about reactions, we are talking about diffusion induced aggregation. So in fact we should be able to get even this constant, rate constant, which is purely coming from a diffusion of the particles. So what I am going to do in this class is to get an expression for the rate constant K, which characterizes the collision probability, the collision rates of aggregates of size A and J. Once we know this, then we can set up chemical master equation equivalent number balance equation, which I call population balance, and then we can solve this analytically in some cases, and then we look at what is the final analytical solution for the concentration of these species. Okay, so that's a roadmap. Okay, so now the first task is to any question at this point? Is the problem statement is clear? Sorry. So here you can model this as a jump process if you like, but here I am treating this as a continuous Markov process. Okay, so space is continuous, and if you remember in the chemical master equation, we consider this as a jump process because this process itself is a jump process. Okay, so you have the option of doing both ways. So in this case, I'm going to define number concentration as a stochastic variable here. Okay, so I'll come back to this how I'm going to, when I show this equation you will know, but before we do this, let us look at how to estimate this constant, rate constant. The rate constant is a collision rate constant between two aggregates of size I and j. So the first task is to calculate the collision rate due to diffusion. Okay, so here I'm going to use the Fokker-Planck equation for this problem, but I'm going to make some assumption about how I'm going to set up the problem. Okay, so here I'm going to consider one particle frozen in space. This particle is frozen, fixed. Okay, and now I'm also going to define a coordinate space in the radial direction r. Okay, so the coordinate system is centered at the frozen particle's origin, and then the azimuthal and polar symmetry is assumed. You are looking at only in the radial direction. Okay, how the particles, the neighboring particles are going to diffuse around. So now I have all the other particle diffusing about. So initially all the particles have the same size, and I know its initial concentration. Now all these particles are allowed to undergo Brownian motion, free Brownian motion in the coordinate system that I am taking as a radial coordinate system with respect to the center particle. So let's actually highlight this particle. This is a frozen particle. So now what happens is, when these particles, when they freely diffuse around, whenever any one particle comes very close to this, it will aggregate to this. Okay, so essentially sitting at the particle center, I am asking what is the rate at which particles are coming towards me. That is going to tell me the rate of collision between this frozen particle for a given concentration of the neighboring particle. First we will get that, then we will remove this assumption that this particle is not fixed anymore. This can also undergo Brownian motion, because in reality all particles are moving about. But for the mathematical treatment of this problem, we are doing it in two stages. In the first stage, we tag one particle, keep it frozen, and then you ask what is the rate at which the neighboring particles are colliding with this, that we can estimate. Then second stage, we remove this assumption this particle is frozen, we will let this particle also diffuse about, then we will calculate what is going to be the rate of collision between two pair of particles. Okay, so that's the idea. Okay, so now with regard to all the other particle, diffusion of these particles are governed by free diffusion or the Fokker-Planck equation with the characteristic function A equal to 0 and B is equal to 2D. Wiener process for the other particles. Okay, so we would write dou P by dou T, A is 0, so you will have something like this in this case, right? But this is written for a rectangular coordinate system, but now I already said I want to do it in a spherical coordinate system. So this I am going to write differently. So this is first time where we are moving from a rectangular coordinate system to some other coordinate system, in this case spherical coordinate system. Why I am doing this? Because I have defined my problem such a way that the coordinate system is centered at the origin of this frozen particle, and I am looking at only the radial variation of concentration from this point of view. Okay, so then the Laplacian operator or the second order differential term that you see here is written now in the radial coordinate system. Okay, if you want to look at other if you have anisotropy in the azimuthal and polar angle, you can have other terms also here. But here we are seeking as analytical solution. The simplest thing you can do is look at only the radial variation. Okay, so you're looking at from here at r equal to 0, you're looking at radially outward and you're asking what's the probability of finding a particle p. Okay. Now this is written as if you have one single particle and you're finding the probability of finding a particle at r which is undergoing free Brownian motion. You can also write this equation in terms of concentration. If you define n of r comma t something like this. So all this p here can be written in terms of number density or concentration also. Okay, then we would call this as a diffusion equation. In chemical engineering, we are all familiar with that. Diffusion equation written for a spherical coordinate system. Okay, all right. So what we have got? So we got the Garning equation, and if I solve this, I will get what is the probability of finding a particle undergoing free Brownian motion at r at t, starting from here. Okay, that's what this equation will tell you. But to solve this, we also need boundary conditions. Okay, so what we will see is that the boundary conditions so after substituting here, you would write let's say dou n by dou t So this equation and this equation are the same thing. So here we are writing in terms of probability of finding one particle. So here we are writing in terms of if there are a certain concentration of particle, this gives you what is the concentration of the free Brownian particle about this frozen particle. Okay, this equation are basically analogous. Here we are writing in terms of probability of finding a single particle. So here on the other hand, we are saying concentration or the number density of the particles. Okay, so now the boundary conditions. So as I said before, if these particles come close enough, okay, the moment they come here, they would get attached here. Okay, so that basically means the particle will vanish. It's not available anymore. It's like a absorbing boundary conditions. Okay, once a particle come close enough to this at the surface, this particle vanishes. It is absorbed. It is not available anymore. Okay, that's one. And then for r at a very large distance, we will have some average concentration of this particle. Okay, so those are the two boundary conditions. I think I have written in terms of n. Yeah. So we say n equal to 0 at r equal to r for all time t greater than 0, and then we say n is equal to n naught for all r. Okay, so with this conditions, this partial differential equation is solved, and then I will give the final result. So n of r comma t So you can see that this solution is quite different from the Wiener's problem. In the Wiener's problem, where we looked at free diffusion in infinite medium, we got a Gaussian distribution for the probability and the concentration. Same Garning equation, but different boundary conditions. There is an absorbing boundary condition at r equal to r, small r equal to capital R. That gives totally different kind of solution. Okay. So this is analytical solution for this particular equation. Yeah. Second, So what I'm saying is, at time t equal to 0, everywhere the particle concentration was n naught, average concentration, right? Initially, hmm. Hmm. Remember, this is not number, it is a concentration. This n naught here, these are not number, these are concentrations, number density, number per unit volume. Okay. Okay. So I have not shown the derivation of this equation, that is not very important right now. So we have to only understand how we set up the Garning equation, what are the boundary conditions. Now we know how the concentration of these neighboring particles change with respect to r and t. Okay. So now what we are going to ask is, we are going to ask, what is the flux of particle coming to the boundary of this particle, okay, and that is basically the rate of collision between this particle, frozen particle, and all the other neighboring particles. This can be obtained by looking at what is the flux of particle at the surface of the surface of this particular frozen particle, and flux is something we can calculate because I know the concentration. I can use Fick's first law and get the flux. So let us say this r, capital R, is a radius of the particle, okay, and this rate of arrival of all the neighboring particle is nothing but the flux calculated at the small r is equal to capital R times the area. Area is nothing but the area of this particle, okay. So this area is 4 pi r square. This flux J is nothing but minus d dou n by dou r calculated at r equal to capital R. Okay, this is Fick's first law, that if I know the concentration, number density of the particle, the derivative times diffusivity minus d, this gives me the flux, okay, diffusion flux, because here the only mechanism by which the particles are coming is by diffusion, no convection here, okay. So this is a diffusion flux. So now you see I have already got n as a function of r and t. What I should be able to do is take this n derivative with respect to r and then evaluate that differential at small r is equal to capital R, okay. And if you do that, and then you have this 4 pi r square, so you would get so when I take the partial derivative of n with respect to r and estimate at small r is equal to capital R, then you will get this term. So what is this k? So this k tells me that if I have a frozen particle at the origin, okay, it tells me what is the rate of arrival of particles on this surface, because those are the ones that are going to aggregate with this particle, right. And so now generally you see there is a time here, meaning that this rate constant is time independent, but then if you look at some time t much greater than r square d, do you recognize what's r square d? R square by d, what is this time scale? It's a diffusion time scale, okay. This tells you how much time a particle takes to diffuse its own particle radius. So if you're looking at time larger than this diffusion time, then this quantity is not relevant, okay. This is important only at some short time behavior, okay. So then you get much simpler expression, that is this should be r here, So, this would be the rate of collision between the neighboring particle onto a frozen particle. Okay. So, the rate constant is obtained only by diffusion here. Okay. So, this purely by diffusion. Hope you studied something called this diffusion controlled reaction, reaction control. I mean, when we think about rate constants, we say diffusion controlled or reaction controlled. Okay. So, this is one example where the rate of the process is controlled purely by diffusion encounter. So, now as I said before, we are still in the first stage where we have frozen a particle and we are asking what is the rate of collisions. Now, in the second stage what we do is we let this particle also diffuse around, just like all the other particle would do. However, the boundary condition is also valid for this particle. Whenever this particle goes to another particle, it is going to aggregate. Okay. When you make this particle also diffuse around, what happens is this K basically gets modified into simply this. It's just matter of it's basically a factor of 2 that's multiplied in this freely diffusing particle. So, now we have the final situation where all the particles are undergoing free diffusion. Whenever a pair of particles come close enough, they will aggregate. Okay. For this process, the rate of collision between a pair of particle is given by this. Okay. One particle diffusing and then there is n number of particles outside. We are looking at what is the rate at which they are going to collide with each other, purely diffusion controlled. So, we will say this is frozen particle, this is a mobile particle. Sorry? As I said, you probably came late. In the beginning, we talked about a case where the center particle was frozen and we got this expression. If you make the first particle, the frozen particle also diffuse around, the rates will be increased. Okay. In fact, there is a model to explain from here to here that I am skipping. So, now this can be now generalized. Suppose if you have Ni concentration of cluster size I and then Nk as the concentration of cluster size K. So, what we did here is with respect to single particle monomer, okay. But like I said in the beginning, the process does not stop at monomer interactions. Monomers grow into dimer, trimer and etc. The larger size aggregates will happen. They also diffuse, they also collide, they also aggregate. So, we are seeking a more general expression for K that involves clusters of other sizes. So, let us say I have a cluster of size I, cluster of K, and the respective concentrations are Ni and Nk. Now, if you ask what is the rate of collision between these populations, and that can be written more generally as the following. Like this, where this dik is basically sum of the diffusion coefficient di and dk. So, this so what we are saying here is di here, this is the diffusion coefficient of a cluster of size I, this is the diffusion coefficient for a cluster of size k, and similarly this rik is basically average of ri plus rk. Yeah. 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 Because I mean, I'm skipping some of the intermediate steps here from this general to this, okay. So that I don't want to deal too much about the derivation. So we'll just take this as a final result, okay. So in fact, I mean, if you substitute di and dj 1, okay, you will get the same answer like before. What we dealt with a single monomer, we are actually generalizing for any sized aggregates, okay. So no, there I was thinking about only one particle with respect to one particle which is frozen or mobile, okay. So here we are talking about the total, all possible collisions and all possible combinations. That's why I was trying to say the stages of how we arrived at. First, frozen particle and finding out the rate of collision, then letting this frozen particle move about, okay. And now we are saying that if there are not just one particle, there is a concentration of particle in each class. I have got Ni constant, not one particle, there is Ni concentration of ith cluster, Nk number of kth cluster. What's the total rate of collisions of all possible pairs? Yes, exactly, yes, because I have talked about one particle. So here we are generalizing for any given concentration. So why we do this is because when we write this chemical master equation for aggregation, we would deal with the concentrations of each species, okay. So that's what I was coming at. So we say this is called the population balance equation. It's actually same as chemical master equation. Same as. So here we write the rate of change of cluster of size k due to this aggregation. So by form, this looks very similar to the chemical master equation. So what we are saying is a cluster of size k can happen whenever two populations colliding with each other such a way that I and j should be equal to k, okay. Suppose if k is 10, you have different combination of collisions leading to a cluster of size 10, 1 and 9, 2 and 8, 3 and 7, etc., etc. So this term captures that, okay. And whenever a cluster of size nk collides with anything else, it is going to be a loss term, okay. So that is this, and you can see that I am using this 4 pi dij drij that I obtained for the collision rate, okay. So this is the rate of formation of cluster of size nk, and this is the rate of depletion or rate of loss of the clusters. So now if you want to solve this analytically, we need to make some assumptions. We will say that d ij is di plus dj is equal to simply 2d and rij as r. This is strictly valid at a very small time. At a very small time, you have only monomers, all particles are identical. So then dij is nothing but 2 times d and rij is nothing but simply r. But as time increases, the particles will have different sizes, then this assumption is not valid anymore. So, if you are seeking an analytical solution for this, you can only solve this analytically at a very short time, where you are starting with the monomer and you are looking at only few aggregation steps. Whereas, if you want to solve this otherwise for a more general case, it has to be only by numerical method. There is no general analytical solution for a general case. Okay, and this solution is given by what we Stochastic. So, once you substitute all that, you will see dnk by dt is given as 8 pi d r 1 by 2 like this. This one? No, see why I put infinity, because this is written for any time. Okay, this aggregation is actually an infinitely happening event. So, you do not really put an upper limit to the aggregation. In fact, aggregation will continue until the entire particle become one single particle. That is when the aggregation stops, and that limit we say something like infinity. Okay, meaning that if you have like one particle and all the other particle minus 1, that will be the last collision step. Okay, even that is taken care by this. So, this infinite basically means that the entire system can actually become one single particle at some point of time. Okay, in fact, I mean, if you want to numerically solve, you will put an upper limit and then you truncate it, because you never have a cluster size beyond certain maximum number. But for theoretical treatment, we can always put this in infinity. So, now next step from here is what you do is you basically sum all possible k and do this here also. So, here we are summing over k is equal to 1 to infinity over all possible k. See, this number will actually, this concentration will decay, because there is a continuous aggregation happening. So, we will call this entire term as n. dn by dt. Okay, so this basically sums the concentration of all the species. This is like a total concentration. Okay, and on the left hand side you will get so we are introducing two things. One is we write the sum of all n as this capital N, total concentration, and then the time t is non-dimensionalized with respect to this factor of 4 pi r d n naught. Okay, so this is a non-dimensional time constant. Then finally what you get is basically like a second order rate equation, okay, which tells you how the total number concentration varies with respect to time. So, if you solve this, you will get n of tau as n naught by 1 plus tau. Whereas if you want to solve n of k, this becomes n naught this is what I was proposing in the beginning, that we are interested in calculating the number concentration of each cluster size k. Okay, so k can take value 1, 2, 3, 4, etc., etc., and this depends on this tau, which is the time constant given by this. Okay. The total n, this will decay by 1 by tau, that is this. And then if you look at the other species, for example n1 will also decay. N2 initially it's 0, but then it will grow, and then this also will decay, and N3, N4, etc., etc. Okay, larger population forms later, goes through typically some maxima, and then they will also decay further. Okay, but the total number will keep on decreasing anyway by this. What I am plotting in each of those curves here, this is like N1, N2, N3, N4, and so on. Okay, yeah, you have something? Yeah. Yeah. You have to do numerically. So the analytical solution is only possible for the very beginning of the system, where you start with mostly monomer. Immediately after that, in a very short time scale, but that time scale can be larger than your diffusion time scale. Okay, so we are talking about some sort of sweet spot, the time such a way that it is not smaller than the diffusion time, at the same time it is not long enough that clusters of other size start happening. Okay, or in other words, the assumption about how Dij and Rij, how we define that is basically is what limits to what extent we can apply these equations. Okay, so just to summarize, what we did here is this, what we did today, that problem has to be taken together with the previous problem we did, where we looked at sedimentation of an independent particle in a gravitational field, okay, by diffusion. So here on the other hand, we do have a concentrated system, no gravity, yet particles can aggregate due to some sort of interactions. Okay, I didn't talk about the interactions, van der Waals interactions, electrostatic interactions. That is, that's something we just brush it under the carpet. So, but we do understand there is going to be van der Waals interaction between the particles. When they come close enough, they will going to aggregate. Okay, so now what we said, this rate of collision due to diffusion can be quantified. The rate constant can be calculated by applying Fokker-Planck equation, continuous Markov process. That is one. Then we go to this chemical master equation approach to calculate this aggregation process as a jump process, right, where the rate constant actually is fed to this. And then in some limited conditions, we can also get an analytical solutions. Okay, so, and for more general case or more experimentally relevant case, you have to do numerically, or you have to do some other approaches. Okay, this one. So what you do, you go back to the original equation, you solve for n1 and n2. Okay, when you do n1, n2, n3, you will get a recursive relation. You will keep substituting n1 in n2, n2 in n3, and so on. So then you can actually get a recursive relation like this. So for other, for further discussions, you can see my notes that I'm going to upload today in the Moodle. Yeah. So I have given the solution, but I have given the reference where the original derivation was carried out. Yes, yes, yes. In fact, I mean, if you take any heat transfer book or a mass transfer book talking about diffusion, people solve diffusion equation under different boundary conditions, absorbing, reflecting, various coordinate systems. So these are basically some standard results that you can find from those handbooks. Yeah, because it's a simple Laplacian equation. So heat transfer, for example, this equation we use in heat transfer also, heat conduction. Similarly, mass transfer also. So there are handbooks to give solutions of these equations for different boundary conditions. Again, you are going to use some of those standard methods, variation, separation of variables, Laplace transform, or do some sort of a similarity transfer. Those standard techniques.